Good morning, everybody. So in the previous class, we looked at the Butterworth filter, and then we start looking at the Type 1 Chebyshev filter. And when we looked at the graphs for the Chebyshev function, this is the graph for zeros, first, second, all the way to the fourth order function. And therefore, based on this graph, we're going to make a few observations. But you can see, although the graph does not extend beyond the 1.5, negative 0.5, but you can see between negative 1 and 1, all these functions are restricted to small values. And then after the 1 and negative 1, the curves go up and have much higher value. So therefore, we can make few observations based on these functions, and that is, let's add it to the so continuing. And did we make any observations back then? Okay, we did. Yeah, okay, we already wrote these things. So we have all these observations that we have here. When x is between 1 and negative 1, the function is between 1 and negative 1. And then when x is greater than 1, the magnitude of x is greater than 1, the function keeps increasingly all the way to infinity as x increases. So therefore, if we take these functions, these Chebyshev functions, and plug them into our filter and look at the relationship between the Chebyshev polynomial and the Chebyshev filter. So looking at the relationship between the Chebyshev polynomials and filter. Our filter, the frequency response of our filter is given by 1 over 1 plus epsilon squared multiplied by t sub n squared of omega over omega cutoff. So we can see that when omega is less than omega cutoff, then the Chebyshev function Tn squared of w over omega c is going to be less than or equal to a 1. Because when omega is less than omega c, then this argument here is going to be less than 1. And remember in the graph, when x is less than 1, the function is less than 1. So this means that if I look at the magnitude of the frequency response, is going to be 1 over 1 plus epsilon squared, the frequency response of j omega squared is going to be between 1 and between 1 over 1 plus epsilon squared. So if this function is a 0, it's going to give me the maximum magnitude of a 1. And then when this function is a 1, it's going to be 1 over 1 plus epsilon squared. Because again, the range when omega is when omega is less than omega c, the Chebyshev function is going to be between 0 and 1. Okay. When omega is equal to omega c, then Tn squared of omega over omega c, what is this going to equal to? It's going to equal to a 1. I'm going to have omega c over omega c. Tn squared of 1 is always equal to a 1 from all these graphs that we have here. It's always equal to a 1. So therefore, this means the frequency response that I'm going to have, h of j omega, is going to equal to 1 over 1 plus epsilon squared. And then when omega is greater than omega c, the function Tn squared of omega over omega c is going to increase quickly. And therefore, the magnitude of h of j omega squared is going to approach 0 quickly. Is that clear? Makes sense? So just from the properties, from the graphs that we generated for P of n, we can observe all these observations. Okay. So therefore, if I look at the frequency response of our filter, it's going to look something like this. 1, 2, 3, 4. And the frequency response h of j omega is going to have a shape that is similar to this. We're going to have ripples when omega is less than omega cutoff, and then it's going to go down to 0 when omega is greater than omega c. So this is my omega cutoff, this is my omega. And at this point here, what is the value of the function here? Agree? When omega is omega cutoff, this is going to equal to square root of 1 over 1 plus epsilon squared. Before it, we have these ripples, and after it is going to decay without ripples. Now, one thing just I want to mention here is that we can know the filter order by counting the number of the ripples that we have here. So you have 1, 2, 3, 4, 5, 6, 7. So as we will see, this is a 7th order by counting these ripples. How many ripples we have here? Okay. Now we're going to define this distance as delta, and this is going to equal the ripple magnitude. So therefore, let's write a few observations or some properties of the Chebyshev filter. The first is that the ripple factor epsilon controls the amount of ripples and the steepness of the drop. So as epsilon increases, we're going to have a higher magnitude ripples. And this is bad. However, the drop off is going to be steeper, which is good. Together? Epsilon, this epsilon factor, the higher, the bigger the ripples are, and the higher the drop-off, or the steeper the drop-off. The second observation is that the number of ripples equals the filter order. So in this case, we have 7 ripples. So this is a 7th order filter. And the third observation, R equal passband attenuation. We're going to define the passband attenuation is going to equal the ripple magnitude in dB, and it's going to equal to 20 log 10 of square root of 1 plus epsilon squared, which is going to equal to a 10 log 10 of 1 plus epsilon squared. Together? So we plotted this in magnitude, but if I were to plot this in dB, then this R, this will represent R. How much? The square root of 1 plus epsilon squared in dB is going to represent the passband attenuation. Okay. So if R is equal to 1 dB, which means I have a passband attenuation of 1 dB, then I can calculate the ripple magnitude delta, and is going to equal to 0.10875, and that will correspond to an epsilon that is equal to 0.50885. And if I have a ripple magnitude that is equal to 1/2 dB, then that's going to correspond to a delta that is equal to 0.05594, and that will correspond to an epsilon that is equal to 0.34931. And to get these numbers, let's do it for this one. If I take 1 over square root of 1 plus 0.50885 squared, this is going to equal to 0.8913, and therefore delta is going to equal to 1 minus 0.8913, which is going to equal to 0.1087. And epsilon is equal to 10 to the power of 1 over 10 minus 1, which is going to equal to 0.50885. Is that clear? Makes sense? Everybody? So we can calculate, if we are given R, we can calculate epsilon is going to equal to R over 10 minus 1. That will give me an epsilon, the epsilon value, the 0.508. And then from epsilon, I can calculate the magnitude. If I subtract it from 1, it's going to give me a delta. Make sense? This is according to our definition. This is what the delta is, which is the 1. This magnitude here is a 1. We have a normalized filter. So the magnitude at 0 frequency is a 1. The difference here, we defined it as the ripple magnitude. So 1 minus 1 over 1 plus epsilon squared is going to equal to R, to delta. Together, everybody?
Let's write it down.
Go ahead.
So even if it's first order, is the stop band still smooth like that? Like there's no ripple?
The stop band, yes, is always smooth.
Oh,
The pass band will have as many ripples depending on the filter order. But the stop band is always going to be with no ripples. Is that surprising?
There's
it
a
sh-
diagram you drew a while back that had, I saw ripples in the.
we'll
stop
have
band.
something that will have ripple in there.
Would that be more efficient? Is
Uh,
there a filter that's more efficient that?
Well, this one is more efficient than the
Than the
Butterworth in terms of the filter order.
Mhm.
I mean, that's how we're defining the efficiency. Makes sense? It will have a lower filter order than the Butterworth. Now, this filter has ripples, and we'll see if we look at the Chebyshev type 2, where are the ripples going to be?
Oh, in the stop band.
In the stop
Okay.
Okay, so this should come as no surprise, because we've seen it here. Here we have ripples when x is less than 1, which means omega less than omega c, there are ripples. After omega is greater than omega c, the curve is smooth. There is no ripples anymore. Okay. Now one more thing to mention. Go ahead.
Epsilon be the square root of that?
Yes, it must be. Epsilon squared.
That's how we the square root of that. Of 10 to the 1. 10 minus 1.
Okay.
The whole.
Square root of, I think square root of that, which is going to equal to 0.508. Good observation. This is r over 10 minus 1. This is, I'm giving epsilon squared.
Yeah. Square root of that.
Okay. One more thing to mention, and we're going to just mention it briefly and just run MATLAB to show it, which is the Chebyshev filter will have n poles and no zeros. And the poles lie on an ellipse and therefore if I were to plot the poles of our filter, they're going to look something like this. Together? So unlike the Butterworth, how did the Butterworth poles look like? Anybody remembers?
Like a circle, right?
On a circle. For the Chebyshev, the poles fall on an ellipse. So if we were to run the MATLAB, that that's not what we want. That's not what we want. This is what we want. So you can see here, this is 1, 2, 3, 4, 5. If I count them all, 5 poles, and therefore a fifth order filter poles location. And again, if you were to plot these locations, you'll see that they fall on an ellipse. So I'm going to paste it here, and I'm going to paste the code for it, so you can generate them if you like for any order. Yeah, it's a fifth order, n equal to 5. Okay. I update this MATLAB code from my office because they're on the Google Drive. But I'm always worried Google did not sync. And therefore, I have to check, make sure that it's has synced. Okay. Now what we can always do, if we need to find the poles, is we can always go to the tables of the Chebyshev filter. So here is the polynomials for the Chebyshev filter for different values of ripple factor. And here are the poles of the Chebyshev filter for different values of the ripple factor. So usually these are available as tables that you can use. And I'll have them in the handouts here. Okay. So let's look at how we design a Chebyshev filter. Now, also keep in mind that all the filters that we are designing are of what type?
Low pass.
Low pass filter. Is anybody bothered by that? No? Nobody ever planning on doing a high pass filter, a band pass filter?
We'll get there.
We're going to get there, yes. We're going to see that once we design a low pass filter, we can transform it into any other filter. So if you know how to design a low pass filter, we should be able to generate any other filter. Okay. So if I design a Chebyshev filter, we're going to be given the cutoff frequency, the stop frequency, alpha, which is the minimum stop band attenuation, in dB, and we're going to be given R, which is the passband ripple in dB. What is the new factor that we have now that we did not have with the better word?
R.
Excellent. R. Is that a good thing or a bad thing?
If you're fine with that trade-off, it's fine.
I mean, more options is always better. Make sense? Okay, so the first step is we're going to determine the ripple factor epsilon from the passband ripple specification. So given R, we can calculate R is equal 20 log 10 H of C at J omega C. And we want this to equal an R. And therefore, since H C of J omega is equal to 1 over 1 plus epsilon squared Tn squared of omega over omega C underneath square root. This is going to equal to a 10 log 1 plus epsilon squared equal to R. Is that clear? Everybody, we went from this to this. We have a square root here. It's going to make the 20 10. And this is in the denominator. We make it to the numerator. It's going to give me a negative sign, so it's going to become positive 10. Okay, so therefore, epsilon is going to equal the square root of 10 to the power of r over 10 minus 1. Okay. Now notice that R is independent of the filter order. So this is going to give me, or epsilon is going to be independent of the filter order. The second step is to determine the filter order. And we're going to determine that from the stop band attenuation. And therefore, we want negative 20 multiplied by log 10 of h c of j omega at the stop frequency to be greater than or equal to alpha. Together, everybody? And therefore, we want 10 log 10 of 1 plus epsilon squared Tn squared of omega stop divided by omega cutoff to be greater than or equal to alpha. Again, because there is a square root, and because it is in the denominator, that negative 20 becomes a 10. Okay, so we can calculate Tn squared of omega stop divided by omega cutoff. What is this going to equal to? It's going to be greater than or equal to 10 to alpha divided by 10 minus 1 and divided by epsilon squared. Agree? So therefore, we're going to select n such that this condition is satisfied. Such that Tn squared of omega stop is greater than or equal to 10 to the power of alpha over 10 minus 1 over epsilon squared. The next step is we're going to find h of s. Where are we going to get the h of s from? From tables. And usually the table is going to have r equal 1 and 1/2 dB. And finally, we're going to unnormalize. We're going to replace S with S over omega C. Okay. Let's do an example and do these calculations. Okay. So, as an example, when I determine h of s for a low pass Chebyshev type 1 filter to meet the following specs. We have omega cutoff that is equal to 10 radian per second. We have R that is equal to 1 dB. And we have omega stop that is equal to 25 radian per second. And we have alpha that is equal to 40 dB. Okay, what is the first step? We're going to calculate the value of epsilon. And epsilon is going to equal to the square root of 10 to the power of r over 10 minus 1. And this is going to give me a 0.50847. Okay. We're going to calculate omega stop over omega cutoff, which is going to equal to 2.5, the 25 over 10. And therefore, I'm going to plug it in Tn squared. So we want Tn squared at omega stop over omega cutoff to be greater than or equal to 10 to the power of alpha, which is a 40, over 10 minus 1 over epsilon squared. And if I calculate this value, this is equal to 38,617.32. So therefore, we want Tn of 2.5 to be greater than or equal to 196.53. Together? So this is reduced to finding the polynomial that is at 2.5 is going to be greater than this. Now we have the list of all the polynomials for Chebyshev. So I'm going to come, I say, okay, is it a first order? I'm going to calculate T0 at 2.5. This is equal to a 1. I'm going to calculate T1 at 2.5. If you remember, T1 of x is just equal to x. So this is equal to 2.5. I'm going to calculate T2 at 2.5. This is equal to 2x squared minus 1, which is going to equal to 11.5. So it's not. T3 at 2.5 is going to equal to 4 multiplied by 2.5 cubed minus 3 times 2.5, which is equal to 55. That is not. We're going to calculate T4 at 2.5, which is going to equal to 8 multiplied by 2.5 to the power of 4 minus 8 multiplied by 2.5 squared plus 1, which is going to equal to 263. So this is the smallest n that will satisfy the condition that Tn at 2.5 is greater than 196. So therefore, n is equal to 4. Okay, so what we're going to do next is we're going to go to our Chebyshev table. And we're going to get the polynomial. So we're going to come here to our Chebyshev polynomial. R is equal to a 1. And we are given this fourth order. You cannot see the numbers here. But this is the structure of the polynomial. So therefore, I can write this polynomial from the table. And that polynomial is going to be given by h of s. So here from tables, h of s is going to equal to 0.2756 divided by s to the 4 plus 0.95 s cubed plus 1.4 s squared plus 0.74 s plus 0.2756. What is the last step? And normalize it. And therefore, we can calculate h of s. So this is normalized. And h of s is going to equal to 2756 point something over s to the power 4 plus 9.5 s cubed plus 145.3 s squared plus 742 s plus 2756 1.453. Together? Because omega cutoff is at 10, I'm going to be dividing by s over 10 to the power of 4. Everybody sees how I'm multiplying by 10,000, numerator and denominator? Yes? Anybody? Anybody does not see it? We went from here to here. Anybody? Too shy to ask or not paying attention? So again, what we do here is we're going to take 2.2756 and divide it by s over 10 to the power of 4 plus 0.95 s over 10 to the power of 3 and so on. And then we multiply numerator and denominator by 10 to the 4.
Yeah.
So I'm going to end up multiplying the numerator by 10 to the power of 4. So the 0.2756 is going to become 2756. Okay. We can check that our filter is correct by plugging the magnitude at 25. And that magnitude is going to equal to 0.008368, which is going to equal to negative 41.55 dB, which is greater than 40 dB, which is what we want. Okay. Sorry, I'm going to move it to the side.
How do we convert the decimal to the dB
Decimal is dB.
of the decimal?
0.0.
20 log 10
All right,
of
yeah.
that value. Okay. So if you look, this is our filter that we just designed. What order is this filter? What is it?
Or
4. How do you know it's 4?
ripples.
No, because we just
Yeah,
we don't design
before,
it.
we can also double check by.
But we can also get it from you. 1, 2, 3, 4. Now this is the plot of the magnitude, not in dB, and this is in dB. And you see in dB, these ripples get much smaller. Okay, but we can see also when it is 25, it is less than 40 dB, which was the requirement that we have. Make sense?
Yeah.
Okay. Okay, great. So now we know how to design a Butterworth filter. We know how to design a Chebyshev filter. So let's look at the advantages of the Chebyshev filter. What is the advantage of the Chebyshev filter?
It's more efficient.
It is, yes. So the first advantage is we have additional design parameter. Which was the epsilon. So this gives us more flexibility than a Butterworth filter. And the second advantage, for a given design specification, the order of the Chebyshev is going to be less than or equal to that of the Butterworth filter. Together?
Does it say less than or equal to?
Less than or equal to, yeah. So it have a lower order than that of a Butterworth filter. Now, probably I should mention something about these ripples. Is anybody bothered by these ripples here? Not particular? No, we don't have to mention anything.
What do we expect?
But you could have your system so that you can tolerate, these ripples.
Yeah.
You know what I'm saying? So again, it's ultimately up to you. But if you're in passband, it doesn't have to. I really want to attenuate higher frequencies to maximum limit, but I'm okay if the passband gets through a little attenuation. Then these ripples can be tolerated. Okay. What are the disadvantages of the Chebyshev filter?
Yeah.
Which one? We have ripples. In the Butterworth, we didn't have ripples. So we have ripples in the passband, which, depending on the application, might be undesirable. And therefore, if the ripples in the passband are a problem, we can always design another filter, which is the Chebyshev type 2 filter. Now somebody listening or watching is going to see, oh, this is really getting boring. We're gonna go from a filter to a filter, spend all this time just going through steps. And what is my response to that going to be?
Oh, well.
Deal with it? No, we're not going to go through the design steps of the Chebyshev. And we saw the Butterworth, we saw the Chebyshev one, so you got the idea of how we design a filter. So we're just going to mention the other filters. Okay, so this is the equation of the Chebyshev type 2 filter. Now we have the Chebyshev polynomial both in the numerator and we have it in the denominator. And therefore, for omega equal to omega c, the magnitude of h of j omega is just going to equal to 1 over 1 square root of 1 plus epsilon squared. When omega is very small, less than omega c, we're going to have a very large number divided by a large number plus a constant, and therefore this is going to be approximately equal to a 1. And this is just a constant, omega stop over omega. This is omega, that is the variable. And when omega is equal to omega stop, we're going to have h of j omega that is equal to 1 over 1 plus epsilon squared multiplied by Tn squared of omega stop divided by omega cutoff. Why is that the case? Because if I plug in omega stop here, it's going to be omega stop over omega stop. What is Tn of 1? Is equal to a 1. So this is going to be 1. This is going to be 1. 1 over 1 plus 6. Okay. So if I look at the frequency response of the filter, it looks something like this. Go ahead.
For the omega equals omega stop, would it be the quantity magnitude hj omega squared?
Yes, there is a square root. So let's just make this squared. This is 1 over epsilon squared. And we have a cutoff here that is omega stop. Okay. So if you look at the frequency response of the filter, instead of having ripples in the pass band, now we have ripples in the stop band. Okay. Another filter that we can also design in the continuous time domain is the elliptical filter. So again, for all these filters, we're just going to mention them without designing these filters. So this elliptical filter, the frequency response is given by hc of j omega squared equal to 1 over 1 plus epsilon squared un squared of omega over omega cutoff, where un of w is a Jacobian elliptical function. And if you look at the frequency response of this filter, what do you think the frequency response of this filter is going to look like? It's going to have ripples both in the stop band and in the pass band. Omega cutoff and omega stop. Together? What is the advantage of this filter?
Probably even lower order.
Yes, it has the lowest order. Okay. Another filter, and of course this is the advantage, and the disadvantage, it has ripples both in the pass band and the stop band. And finally, the last filter we're going to mention the last filter we're going to mention is the Bessel function, Bessel filter. And this filter, h of s, is given by 1 over bn of s, where bn of s is equal to the Bessel function, which is equal to summation from k equals 0 to n, ak multiplied by s to the power of k, and ak is equal to 2n minus k factorial divided by 2 to the power of n minus k multiplied by k factorial of n minus k factorial. Now this Bessel function, the main advantage of the Bessel filter, it has linear phase in the pass band. Okay. What does linear phase mean? Okay, so here is, I'm going to just put these here, an elliptical filter and a Bessel filter. please try to run them, when you look at the notes, and change the filter order and see how they change. Okay. What does the linear phase mean?
Means no ripples.
What is it?
Means no ripples.
Phase. Anybody? So what happens when we have a system that has a linear phase? This is what happens. So what happens if I apply to a system multiple sinusoidal signals? And then I look at the output of the system. So we have a system here. And I applied multiple sinusoidal signal. This is a sinusoidal signal. This is a different frequency. This is a different frequency. Together? If this system has linear phase, then at the output of this system, all of these sinusoids are going to be delayed by the same amount of time. Together? So if I were to plot a line here, and this is how the signals look at the input, if I look at the output, the magnitude of these signals might be changed. However, the relative delay between them is going to be the same. Does that make sense? Now what happens, this is if it has linear phase. If it does not have linear phase, what's going to happen? These signals are going to be delayed a different amount of time. So I might look at the output of the system, and this signal here might be like this. This signal here might be like this. Make sense? So a linear phase means the group delay is a constant. If you import any sinusoidal signal or any frequency, it's going to be delayed by the same amount as any other sinusoidal signal, as any other frequency. If the phase is not linear, it means it's going to be delaying different frequency differently. Together? Everybody? Is that clear? Okay. So now we're ready to move or to go back to our course, meaning course of travel, and design our digital filters. So remember, all what we've done since probably 3 classes ago, we said we're going to do an excursion. We're going to look at all the analog filters, review them, design analog continuous time filters. But then after we design these continuous filters, I want to be able to come back and design a digital equivalent of them. Okay. So this is what we're going to be doing next. Which is how we're going to take this continuous and convert it to a discrete transformation. So the question is how to transform H of S to a discrete filter that is going to be H of Z. Does the concept make sense? So we designed that continuous time filter, but I'm not interested in a continuous time filter. I'm interested in a discrete time filter. So what I want to be able to design is, or build, is a discrete filter. So we had H of S for the different filters, the better word, the Chebyshev, but I want to be able to get h of z. Now, if we look at this transformation, what are the things that we need to do in order to do this transformation and ensure the integrity of the filter that we're going to build? Okay, I'll give you one, and then you guys give me. We need to preserve stability. Make sense? Like, I don't want to transform a continuous filter to discrete, and all of a sudden the filter is unstable. The filter is such that there is a pole outside the unit circle and the filter is unstable. What else we want?
Keep efficiency.
Okay. We want an efficient transformation, yes. What else?
We want to get back our original HS.
We're not interested in HFS anymore.
Okay.
It's, I don't know if you meant, like, once we have H of S, what I'm really going to do is H of Z. And I'm going to be implementing H of Z. But I guess probably what you meant is I want to preserve the shape of that filter.
Yeah.
I have a continuous time filter that looks beautiful. I want to go back to the discrete time domain. I'm going to transform it to the discrete time domain. I want it to look as good as the one I designed in the continuous time domain. Make sense? Of course, you realize, or not realize, that there is no, if I design this filter in the continuous time domain, it's not like I can just go to the H of S, replace S with Z, and all of a sudden it's a discrete time filter.
Yeah.
Makes sense? This is not, that's how it works. It's going to have to go through a transformation. So the second concern that we have is I want to preserve the frequency response as much as possible. And apparently, I said as much as possible because we're going to see the frequency response is going to be impacted, but we're going to try to minimize that impact on the frequency response. Another concern that we have is we want to avoid aliasing as much as possible. And somebody now looking like, whoa, what's aliasing? We talked about this at the beginning of the semester. How did this pop up? We've been fine without aliasing. Where's the aliasing come into the equation? We'll see it. We'll see what we mean by this aliasing. Hopefully we all understand now aliasing, so once we explain it, will be. And
We have to make sure that the sampling frequency agrees with the filters that we're using.
Sampling frequency with the filter, yes. The sampling frequency is going to have a big impact on how the filter is going to look like. And yes, I want to make sure for that sampling frequency, I'm not designing a filter that because of the aliasing, it's not going to work. Make sense? Anytime we are in discrete time, this is continuous time, we're going to transform it to a discrete time. Apparently, we're going to do some type of analog to digital transformation or continuous to discrete transformation. That means sampling somewhere. Sampling means aliasing. So apparently, the shape is going to be impacted. Again, we'll see it more clearly. And what you mentioned, we want as simple and efficient as possible. Okay. We're going to look at 3 different transformations. So this is what we're going to be doing next. We're going to be looking at each one. So again, if you're lost of where we are, we're trying to transform the continuous time filter to the discrete time domain. The first method is called impulse invariance. Impulse invariance, and this is based on sampling the impulse response. And we'll see what that means. The second method is called matched Z-transform. And this is based on pole/0 mapping. And finally, we're going to look at bilinear transformation. And this is based on mapping to avoid aliasing. Sounds good? Impulse invariance, matched filter, bilinear transformation will help us take a continuous time filter that we designed and transform it into a discrete time filter. So let's start with the first one. Did you finish typing or did I cut you?
I cut it off the end.
Okay. So let's look at the first method, which was the impulse invariance. So what is the idea behind the impulse invariance? We're going to take the impulse response of the designed filter, of the discrete time filter, to be equally spaced samples of the continuous impulse response of the analog filter. Okay, let's see what that means. So the impulse response of the designed discrete time filter is going to equal to, or is going to be, equal spaced samples of the impulse response of normalized continuous time filter. What does this mean? So we designed a Butterworth filter. So if I come here, we designed a Butterworth filter. And how did the frequency response look like? It looked something like this. Agree? We usually plot this from 0 to infinity. So we only plot this part of the filter. But the frequency response looks like this, symmetrical around the y-axis. So this is my h of j omega. and this is my omega. This is 1. This is omega. This was my cutoff frequency. This is what we've done with a Butterworth filter or any other filter. Now, how does this filter look like in the time domain? I can find out. How do I find out the filter in the time domain? Who took control class with me? Where was the Butterworth filter? Oh, here. Here is H of S of the Butterworth filter. How do I know the impulse response of this filter? I know everybody knows the answer. I know what you guys are trying to do. Don't do it. Just answer. You're going to just take the inverse Laplace transform of this. That's the impulse response. Make sense? Impulse response is small h. Take the Laplace of small h. What does it give you? The frequency response, h of s. So what I have to do, come here, take the inverse Laplace of this function. How do I take the inverse Laplace of this function?
Tables.
What else? MATLAB, what else?
Partial fractions.
Excellent, yes. I can come here, do partial fraction expansion. That is going to give me the impulse response of this filter. Please keep this in mind. H of n in the time domain is impulse response. In the frequency response. What did I say? H of n. H of t, impulse response. H of s, frequency response. H of n, impulse response in discrete time. H of z, or H of omega, frequency response in the discrete frequency domain. Make sense? These pairs are always there. So therefore, what I can do, I can come here and say, okay, I'm going to plot a random shape for the time being, but once we do an example, we'll plot the exact shape of how the filter is going to look like in the time domain. So I'm going to come here and say, okay, the filter looks something like this. This is h of t. And let's make this continuous, and this is x continuous. Why did it start at 0? Why did I not plot this like this?
It is going backwards in time.
Meaning?
It has to be causal.
Causal. Excellent. Yes. I want the filter to be causal. So it's going to start at 0. Remember, this is the impulse response. I apply the impulse at 0. The response cannot happen before 0. Okay, what do I have to do now? I can come to this filter that you tell me you like. You designed the Butterworth, the Chebyshev, whatever filter you want. I'm going to take this filter. I'm going to come here, and I'm going to convert it and make it a discrete time filter. How do I do that? I'm going to take samples of this filter. So if I come here, and I take a sample here, a sample here, sample here, sample here, what do I have all of a sudden? Instead of h continuous, in red, I'm going to have h of n, which is going to equal h continuous at n multiplied by t. Agree? Everybody? Are we done? Well, we're going to look at what happens in the frequency domain, because that's the whole point of building the filter. What's going to happen to the frequency domain? If this has this frequency response, or if this is this in the frequency domain, if I come and I sample this, what's going to happen to this?
band limited? Or it's limited in the frequency domain? Because
What else?
is it limited in the time domain? Like when we sampled, because that's,
No, don't get that out of that.
okay.
What's going to happen when we sample any signal? What's going to happen to the spectrum of that signal? It's going to start repeating.
Yeah.
Remember? Sampling.
Periodical.
So what's going to happen is that this curve here is going to all of a sudden look something like this. Here is one. Oh, don't do that. Here is two. Here is a 3, and it's going to go all the way to where? To infinity. Remember, sampling in the time domain is going to cause the spectrum to start repeating. Now, if I plot this against omega, what is this point going to equal to? What is it? If this is W, what is this going to be? Omega s, the sample frequency. So this is going to be at omega s, at 2 omega s, at 3 omega s, and so on and so forth. So this is at omega s, 0, negative omega s. And this continues like this. Together? So what happens? I designed this perfect filter that meets all my needs. I went and I said, okay, the way I'm going to implement it, I'm going to have samples like this. Now all of a sudden, the filters look like this. Is that good or bad?
Pretty bad.
Bad?
That's all good.
Bad or hopeless?
If you want aliasing that much,
Well, we have two choices, bad or hopeless. Which one will you choose?
Just bad.
Bad, this is good. I mean, you did not choose. It's bad, but it can be fixed if we choose this omega sampling to be very large, isn't it? It's going to have minimum aliasing, and of course we exaggerated this overlap. If this is really going very deep, very sharp, then the aliasing is going to be minimum. Make sense?
Yeah.
Okay, how we do that is what we're going to do after we come back from spring break. Enjoy your break. And again, if you're watching this lecture, please send me email and go back to the previous lecture and send me the email that you were supposed to send me from the previous lecture.